Welcome back to a fresh episode of McGrathematics. At the request of Mr. Travis Fuss, here is the return of the McGrathematics theme music. Thank you. So that doesn't get me sued. All right, we're starting off with a flashback question from the complex numbers topic. We're trying to find all solutions to the modulus of a complex number with an argument of 2 theta minus 1 equal to root 3, satisfying theta between minus pi and pi inclusive. Okay, I've seen a few places solve this question using graphical methods, but graphs suck. Why use graphs when you can use good old-fashioned algebra? So what we're going to do is we're going to write the complex number in polar form. So e to the 2i theta. Remember our form re to the I theta. So whatever is with your I in the power is your argument, and whatever is multiplying out the front is your modulus. So we have a modulus of 1, and we have an argument of 2 theta. Now, if we're finding the modulus of this complex number, we want to group together the real part and the imaginary part. So the real part is cos 2 theta minus 1, and the imaginary part is sine 2 theta. Now, we know how to find the modulus of a complex number. We take the real part and the imaginary part, we square them, we plus them together inside a square root. So it looks like this. Okay, this is the square root of x squared plus y squared. Now, this is now our trigonometric equation that we are going to attempt to solve. We can start off by, of course, squaring both sides to get rid of the square root on both sides of the equality. We're going to expand out the brackets, so we have cos squared 2 theta minus 2 cos 2 theta plus 1. So there's our binomial expansion of cos 2 theta minus 1 squared. Okay, now what's convenient is that hopefully you recognize that cos squared plus sine squared, when you have the same angle, that's called our Pythagorean identity. These guys can go together to make a 1. So left-hand side becomes minus 2 cos 2 theta plus 1 plus 1. So what we can essentially do is just take 1 away from both sides, and the cos squared plus sine squared is vanished. Now this is a much simpler equation to solve. We can just take away 1 from both sides to get 1 on the right. We can divide by negative 2, so we end up with cos 2 theta is equal to negative a half. Okay, so if cos is giving us an answer of negative a half, we know that cos 60 gets us a half. So we're looking at cos 60 in the negative quadrants for cosine, which is going to be quadrants 2 and quadrants 3. All right, so in quadrant 2, we're going to get 120 degrees, which is 2 pi on 3. In quadrant 3, we're going to get 180 plus 60, which is 240, aka 4 pi on 3. Now remember that because cosine is an even function, whenever you have a positive value that solves the equation, the negative value will do the same thing. Okay, this is important because our domain goes to positive pi, but also goes to negative pi. That's why I chuck some plus minuses on these two guys. And now all we need to do to finish off is divide both sides by 2, and we get our 4 solutions that are within the range of the domain given in the question. So if you try that yourself and you got positive negative pi on 3 and positive negative 2 pi on 3, well done, you got 3 marks in what is essentially a fake HSC exam from 2020. Okay, for today's lesson, we are up to our 4th lesson in integration, looking at substitutions. If you're not from my class and you're wondering where the 3 lessons before this are, they are on my channel. They're just a bit older. They're from 2020. So the first 3 lessons of integration have been covered in slightly lower quality, but still watchable. All right, today we're looking at substitution. So in extension 1, if there's a question that involves integration by substitution, the question will always, every single time, give you the substitution to use. Whereas extension 2 is a more challenging course. Quite often, if there is a substitution to make, you need to figure it out for yourself, and sometimes be a trial and error when you're first new to it. But yeah, so quite often when you need a substitution in extension 2, they won't explicitly tell you what to do. You've got to know what to substitute and when to substitute it. Okay, we'll start off with some easy ones. For some of these questions, you don't really need to use a substitution if you are really good at spotting the reverse chain rule. But if you're not up to that yet, that's all good. I'm going to go by the step-by-step using substitutions. So for these questions, what we're really looking for is a function being multiplied by some form of its derivative, okay? Because when you make a substitution, part of the derivative always gets subbed out and vanishes, and the question always tidies up really nicely. So looking at this question, I notice that I've got an x cubed up here, and out the front, I have an x squared, which is pretty close to the derivative of x cubed. That's why it's going to be a good idea for me to substitute u equal to x cubed. Because now when I do my derivative of u with respect to x, I get 3x squared. If you want, you can rearrange this to make dx the subject. So I'm going to put the dx across here and the 3x squared underneath here. So these two guys just swap places. And now we have a substitution for dx. So subbing in everything we have now, our e to the x cubed is now e to the u. Our dx is now a du on 3x squared. Like I said, this is convenient because our derivative, 3x squared, is going to cancel out the x squared at the front of the exponential and give us a really nice and tidy integral to solve. So the x squareds cancel out. We can put the 1 over 3 out the front of the integral. And so we have 1/3 of e to the u du. So if you can spot the right substitution, it can turn your question into a really easy integral in a short amount of steps. Okay, the integral of e to the u is just e to the u plus c. So we have 1/3 e to the u plus c. Just like in extension 1, never forget to back substitute what you started with. We don't want to leave our answer in terms of u. We want to sub in that u is actually x cubed, and there is our final answer. Okay, on to our next one. We have sine divided by cosine cubed dx. Okay, so for this one, I'm spotting that on the bottom we have a function of cosine. We have cosine cubed. And keep in mind that the derivative of cosine is negative sine, which is kind of on the top here. So again, I've spotted a function and I've spotted its derivative somewhere in the integral. So that function is going to be a good thing to substitute. Okay, for this one, we're going to make u equal to cos x. This gives us that du on dx is equal to negative sine x. Again, if this is the way you do it, you can swap these two around to get dx as the subject. So we have du over negative sine x is equal to dx. Okay, let's sub in all our information into our integral. So our cos cubed is going to become a u cubed, and our dx is going to become a negative du on sine x. A lot of convenience here. We have the sine x's on top and bottom are going to cancel each other out. We can chuck the negative out the front of the integral. And while we're here, we may as well write 1 over u cubed as u to the minus 3, so we can integrate it using good old-fashioned integration. Okay, so integrating now, we're going to add to the power to make negative 2. We're going to divide by the new power of negative 2. Don't forget your plus c. The two negatives cancel out, and we're going to end up with a half u to the minus 2, or we can write this as 1 over 2u squared, plus c, and then chucking back in that u is of course equal to cos x, and there is our finalized integral, 1 over 2 cos squared x plus c. If my voice sounds like 15% more seductive than usual today, it's because I am very, very unwell. But you know what? Maths doesn't take a holiday, so here we go. All right, for example 3, we've got the integral of log x divided by x. So at this point, if you've got some spare paper handy, it could be a bit of fun because math is so much fun for you to write down what you think would be a good substitution in this question. I'll reveal it shortly and you can see whether you were spot on with your reading of the integral. Okay, cool. So my reading of the integral is I've got a log x on the top, and this log x is being multiplied by 1 over x. And what do you know? 1 over x is the derivative of log x. That tells me it's going to be a really smart play here to substitute u equal to log x. So let's do that. U is equal to log x, which means that du on dx is equal to 1 over x. We can just play around with this a bit. We can put the dx across here and multiply the x across to the left. So we have x du is equal to dx. Okay, so now we're going to make the top of the integral equal to u. We're going to make the dx equal to an x du. And again, this was a nice one because all the x's cancel out nicely, leaving us with u du, which is, as far as integrals go, it's a pretty easy one. So we're going to increase the power by 1, so we're going to have u squared divided by 2 plus c. Now we just back substitute in our u equal to log x. So we have half log x squared plus c, and there is your answer. Okay, beautiful. Let's move on to the next one. Getting a little bit spicier now. I've got the integral of root x over 1 plus x. Again, if you're playing along, write down what you think would be a smart substitution here and see if your idea is the same as mine. Sometimes for questions like this, there isn't one correct answer, but there's often one substitution that's going to get you there in the quickest and easiest way. So a good idea here would be to substitute u equal to root x. What I'm going to do here is do that in a really sneaky way. I'm instead going to substitute u squared equal to x, which is kind of the same thing as u equal to root x if we ignore the plus minus. But writing it in this form just makes the algebra a lot simpler. because now we can do what's called implicit differentiation. What I mean by that is we're going to differentiate the left-hand side. So we're going to have 2u differentiated with respect to u. And on the right, x is going to turn into a 1 differentiated with respect to x. Okay? So you don't have to make u the subject and do du on dx if you don't want to. This right here is perfectly legal, and it makes the integral, or the algebra at least, of the substitution just a bit nicer in my opinion. Okay, so now what we're going to have is substituting into our integral. The top is root x, which is going to be equal to u, because if u squared is x, then u is equal to root x. So the top is u. Now on the bottom, we have 1 plus x. Keep in mind that x can be substituted to be u squared. So the bottom is now 1 plus u squared. Our dx, we're substituting to be 2u du. So here's our integral with all our substitutions chucked in. What we can do now is put the 2 at the front and put the u up the top to have u squared. So we've got u squared over 1 plus u squared. Now, this is not a super easy integral, but it is something we have tackled on this channel in previous videos. We're going to do the method what's called splitting the numerator. So I'd really love it if the top of this fraction was a u squared plus 1, because that would really cancel nicely with the bottom. So what we'll do is we'll put a 1 plus on the top, and we'll keep the balance by taking away 1. So I've really only added a 0 to the top of the fraction, and I haven't changed the value of the integral. Now I'm going to split apart these two integrals into two separate fractions. So I'm going to have one of them being 1 plus u squared over 1 plus u squared. And the second one is going to be minus 1 over 1 plus u squared. Okay, so splitting the numerator into two fractions. Keep in mind that that 2 at the front of your integral, it needs to distribute to both of your two integrals when you split them apart. So if you miss this 2 here, you're going to get the question wrong. Okay, now it gets a bit easier because 1 plus u squared over 1 plus u squared is of course just equal to 1. So we end up with the integral of 1 du, take away 2 times the integral of 1 over 1 plus u squared du. Now, hopefully you are an expert in extension 1 integration and you recognize that this integral here can be evaluated using inverse tan. When you have a over a squared plus x squared, you can integrate this as inverse tan of x over a. So our 1 turns into a u and then gets multiplied by the 2. Our fraction turns into inverse tan of u over 1, so we can just write u. Also has a minus 2 at the front, and don't forget your constant of integration. And our last step is to back substitute that u squared is equal to x, which means that u is equal to root x. So we'll change these u's to root x's, and there is our final answer fully integrated. That was heaps of fun. Let's dive into the next one before I pass out. All right, we've got e to the power of inverse tan of x over 1 plus x squared dx. So take a moment, see if you can read the integral and guess what would be the best substitution to make to tie this one up really quickly. Okay, if you are good at reading integrals, you may notice that we have our function of inverse tan on the top, and this is being multiplied by 1 over 1 plus x squared, which coincidentally is the derivative of inverse tan. That tells us that a really smart substitution is to let u equal to inverse tan of x, which means that du on dx is equal to 1 over 1 plus x squared. If we multiply stuff across, we get 1 plus x squared du is equal to dx times 1. So now we have something we can substitute out for dx, and we're going to have only u's in our integral, hopefully. So the top is now e to the power of u for our substitution. We have a 1 plus x squared on the bottom and the top, which is super convenient because they're going to cancel each other out, leaving us with just e to the u du. Okay, super easy integral. We're just going to integrate e to the u as e to the u plus c. Chuck back in that u is actually a placeholder for inverse tan, and there we have our answer for our integral, e to the inverse tan plus c. Okay, charging into the next one, we've got the integral of x divided by square root of 1 minus x. Okay, take a second to have a think about what you'd be substituting here, and then I'll see if my answer is the same as yours. Okay, so similar to example 4, we could substitute u equal to root 1 minus x, but if you want to be a bit sneaky like I am and make the algebra a bit tidier, you can instead substitute u squared equal to 1 minus x. Okay, now we can use our implicit differentiation trick again, just to make this a bit easier. So we're going to have 2u du, so this one differentiated with respect to u, and the other side turns into negative 1 differentiated with respect to x. Okay, what we have now is that if we multiply the negative across, we get dx is equal to minus 2u du. Okay, let's chuck some stuff in now. On the bottom, we have the square root of 1 minus x, which is going to be equal to u, because u squared is 1 minus x. On the top, we've got to play around with this a bit because we need to get an expression for x in terms of u squared. So if we take our substitution and we plus the x across and then minus the u squared across, we end up with this. Okay, I'll say that again. Taking our substitution, add the x across to the left, subtract the u squared across to the right, and we get this right here. That's our substitution for x for the top of the fraction. dx, we're going to substitute minus 2u du, and let's just see what happens. Okay, a bit of a mess, but stuff does cancel out. We can put the minus 2 at the front of the integral. We've got a u on top and bottom of the fraction which we can cancel out. And so we end up with just 1 minus u squared du with a minus 2 out the front. Okay, if we integrate this, 1 turns into u, and then minus u squared turns into minus u cubed divided by 3, plus your constant, and now we just need to chuck back in our substitution. So remember that u is actually equal to the square root of 1 minus x. So we've got minus 2 times root 1 minus x. We've got minus 2 times minus a third gets us positive 2/3 square root of u cubed. So you can put this cubed either inside the square root or outside. It makes no difference. I think it looks a little bit better inside, but it's still extremely valid either way. Don't forget your plus c, and there is your answer. Okay, hopefully that wasn't too quick. I'm kind of in a bit of a fever dream at the moment. Okay, up to our last one, I think. We've got the integral of x to the 5 times root 2 minus x cubed. Okay, keeping in mind the trick that we used from the last example and example 4, write down what you think would be a good substitution for this question. Dun, 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 dun. If you thought to yourself, why don't I substitute u squared equal to 2 minus x cubed to sub out this third term, that is a really smart play. That's what I'm going to do. Okay, so we're going to differentiate both sides. So we get 2u du on the left is equal to negative 3x squared dx on the right. Okay, we're going to rearrange this to make dx a subject, so we have something to chuck in. So we've got dx, if we divide the negative 3x squared over to the other side, we get dx equals negative 2u over 3x squared du. Okay, now let's chuck that all in and see what happens. Oh, and don't forget that, what am I doing here? Okay, cool. All right, so we have, what do we have? Good question. Okay, we have our substitution here. That's our u, because that's equal to the square root of 2 minus x cubed. So that right there was our starting substitution. In the brackets there is just my replacement for dx using our derivative here. So we have dx equal to minus 2u over 3x squared du. Okay, now slight issue here is that some of the x's are going to cancel out, but not all of them. Okay, we're going to put the negative out the front. The x squared is going to cancel out with the x to the 5 and leave us with x to the 3. Oh, now that makes sense. Okay, and u times u is of course u squared. We've got the negative 2/3 chilling out the front, so we don't have to worry about it for now. So now, when you substitute in all your information and there's still some terms in your original variable, you've got to go back to your substitution and get a bit more clever. So going back to here, again, we're going to add the x cubed across the left-hand side, subtract the u squared across the right, and so we get this line right here. X cubed is equal to 2 minus u squared. That's just the top line rearranged a little bit. So now when we go back to our integral, which still has some work to do, we can replace the x cubed with a 2 minus u squared to look like this. Okay, now it's all in terms of u. It's not super complicated. We just got to expand it out and then just integrate and then back substitute, and we'll have our answer. Okay, so we got 2u squared minus u to the 4. Now if we integrate this, we get 2u to the 3 over 3, take away u to the 5 over 5, plus your constant, and don't forget your negative 2/3 was out the front of your integral. When we expand this out, we're going to get negative 4u cubed on 9. We're going to get positive 2u to the 5 over 15 plus c. Now just substitute back in the fact that u is actually equal to the square root of 2 minus x cubed. It's a bit of a mess, but it is a correct answer. Again, like I said, with the cubed and the power of 5, you can put them inside your square root or you can put them outside, depending on what your preference is. Okay, hopefully that made some sense. Thanks for watching if you made it this far. Here are some recommended exercises for anyone trying to get some more practice. In case you're not aware, Howard Mathematics is a free online textbook and it's really, really good for integration. So if you're looking for some more practice, give that a Google, have a go at these exercises, and I'll catch you guys in the next video. Thanks so much. Take care. Bye.